Okay, so we talked about testing then. So what kind of properties do we expect for trees? So how should we test table operations? Well, one suggestion is that we have a much simpler representation of a table, which is kind of more obviously correct. And that is using a list of pairs. And we have some standard functions like lookup for lists of pairs, which we can use to compare the behavior of our implementation of tables with the simple implementation. So we're not comparing how quick they are. That's a separate comparison. We just want to make sure the most important thing is that what we have is correct. And one way to do that is to compare with the inefficient but simple version using lists. So what we need to do is, well, so these are the kind of properties we want, but in order to do so, we need a way of converting between our representation of a table and the simple list-based representation. So we need the contents of a table. We need a function to do that. And if we have that, then these are the kind of properties we expect. If we have a key in a table, then if we look up the key in the table, we get the same result as using the standard lookup function for the contents of the table. And the insert is the same. And I've actually used a function here which we've not seen in the course, but it's a standard function from data.list, which if you give it a number, if you give it a thing and a list of things in order, then it will insert that thing in the right place in that list. So you see I have 2 copies of 7. It inserted it in the right place in this ordered list. So there is a function called insert which will always insert the thing in the right place in a given list if the list is ordered. Okay? So that means when we convert our tree-like representation to a list, we should preserve the order. We should make sure that all those things over there come before this one in the list, and all these things down there come after this one in the list. Okay? So actually, that's pretty much the algorithm. It's pretty straightforward. Let's define it. The contents of the empty table is just the empty list. The contents of a table of this shape, well, we take the element in the middle, these 2 guys, put them in a pair, key and value pair, put those in a little mini list, and then on the left of that, we're going to put the left-hand table, and on the right of that, we're going to put the right-hand table. That is to say, we're going to recursively take the contents of the left and the contents of the right. And that gives us a conversion from our table to a list of pairs. So these properties then, they're the ones that we just talked about on the slide. So I've added the types, because if I don't add the types, Quick Check will choose unit for keys and units for values. And they're really bad values to test with, because unit, there's only one of them. So you will always find what you're looking for. And if you're looking something up, you'll always find what you expect, a unit. You can never do it wrong. So they're really like a really bad way of testing. So you really need to put the types in some way or other. That's one way of doing it. Another way, which is quite common in Quick Check code that I've seen, is not to give the explicit type, but just say, oh, by the way, we'll take keys to be integers and values to be integers. So this is like a dummy definition. We're not really using it. It's just saying we want to test using int. Okay, so that's the testing. But in order to run that, we need to generate random tables. So we need to make table KV, an instance of arbitrary, just like we did with expressions. But because this is polymorphic, what we have to do to make table an instance of arbitrary is we have to assume that K and V are already instances of arbitrary. Because if they're not, we can't generate random tables if we can't generate random keys and random values. So we have a constraint on the instance declaration. We've not seen this before, but basically this just says you can't do this for any K and V. You have to be able to generate arbitrary Ks and arbitrary Vs. Okay, so that's maybe it looks like a little bit of magic. This is the new thing we haven't seen before in the examples that we've looked at. But don't make it too big deal about that. Okay, so here it then is the first attempt at giving the definition of arbitrary. So what's wrong with this generator? Now, this is really testing your memory of the lecture on expressions when we looked at generating random expressions. It went horribly wrong when we tried to do it this way. Does anybody remember what went wrong? Yeah, it kind of grows out of control. So what happens when you do this is that the size of the things you generate becomes really unstable because you have two recursive calls here. These are the two recursive calls: generate the left tree, generate the right tree, generate the left table and the right table. Because there are two of them, things go mad. And these grow way too quickly and they get out of control. So actually you end up sometimes generating infinite things. That doesn't work. So the solution that we used was to add a size parameter to the thing that builds the random structure. So this is what you did with expressions. So I've done exactly the same as was done with expressions. We add a size parameter, so this bounds the size of the table that you will generate. And each recursive call, we divide the size parameter in half. So eventually it will get to 0, which means we'll guarantee to eventually choose the empty. Okay. And then the way we use that, we use the quick check function sized. We give quick check the job of passing the size in. And that's what this guy sized does. Okay. All right, so that's a first attempt. Let's look at the code there. So there's the code that I just described. And there it is. So now we can run quick check. So we can run quick check on our properties. We can quick check prop insert t. Well, let's check the lookup property first and see what we get. Oh, didn't work. It didn't work when we tried to look up 0 in the table which joined the empty table on the left. So where are we? The empty table on the left. The thing in the middle is 1 with value -2. And the thing on the right is the empty table with 0, -3 and empty. Okay, so what's wrong with this example? Well, if we draw it as a tree, what will it look like? I'm looking for Bob in the dictionary, and I find zebra, and Bob is over here. If I find zebra, I say, oh, I need to look left. I've gone too far. Right? So the problem is that the tree is a bad tree. We shouldn't do the structure in a right way. So there's an invariant property that needs to be satisfied for us. We need to generate ordered tables. Yes?
Can't we just generate values and insert them to a list?
Yeah, that's another strategy. That's another strategy. So it's a good suggestion. I'm not going to follow that today, but one alternative strategy is to make sure that if our insert function is correct, we just take a bunch of values and insert them one at a time, they will always end up in the right places. So that's a good strategy, actually. I like that. So in the next version, I might consider using that as an alternative. But here's how I'm going to try and tackle this. It's how I'm going to try and generate ordered tables. I'm going to generate a list, a random list. This will be a little bit easier. And then I'm going to take the first key value pair and put them up here. And then I'm going to recursively look for all of the smaller, the pairs with smaller keys and build a table from those and put them on the left. And all the bigger keys, I'll build a table from those and put that on the right. So the key will be start with an arbitrary list of key value pairs and build the tree in such a way that it's guaranteed to be in the right structure. Okay? So let's have a go at that. So we'll define what the invariant we're looking for is in a minute. But what I'm going to do is define a function which converts a list of pairs into a table in one go. Okay? So if we have the empty list of things to convert to a table, then we can only give the empty table. If we have a non-empty list of things, the first thing in the list will be a key value pair, and the rest will be key values. And the result here will be I'm going to join the table I get from the smaller things with the key values, key and the value, and the table I get from the bigger things, which I need to define now. Okay? So that's the strategy. Take the first thing in the list, put it in the middle of the table. Take all the things where the keys are smaller and build a table from those and put them on the left. And the keys of things which are bigger, build a table from those and put that on the right. So what are the smaller and bigger things? The smaller things are all the key prime, value prime pairs, which are themselves taken from the list KVS, the rest of the things, but not any of them, only the ones for which K prime is smaller than K. So they're all the smaller key value things. And we can define the bigger things in the same way. And it's a bit cut and pasty, but I'm not sure I can find a neater way of doing it than basically flipping that guy there. It doesn't really save us much to define a function for that. How does that look? Yeah?
Wouldn't the tree get really unbalanced if the initial k is really small?
That's right. So here we're going to randomly generate, and by randomly generating, on average, they'll be reasonably balanced. So some will be a bit to the left, some will be to the right. So I know you really want me to talk about balancing trees, but I really am not going to do it today. But it's good that you have it in mind because it is important in the long run. But don't worry about that today. Okay, let me just see that compiles. Yeah, it does. So how do I build an... So now I want a generator for ordered tables. So I'm going to build a generator. That's a do thing. So how am I going to do it? I'm going to take randomly take a list of key value pairs. Okay, so let's assume I can do that. I take the key value pairs from arbitrary. Now that will only work if the keys are in arbitrary and the values are in arbitrary. So I'm going to need a type constraint on this. What I'm trying to do in this function is write a generator for tables for some type key and some type value. So the ordered table type, I want something like this, but it will only work if the keys are in arbitrary and in the values are also in arbitrary. So arbitrary key, we can generate arbitrary keys we can also generate, arbitrary values. And there's one more constraint. Does anybody see what the other constraint is? Yeah, the keys must be ordered. We're going to compare keys. So we also have a constraint ord k. So the type is pretty kind of hairy, but never mind. We're going to return. So once we're able to generate a random list of key value pairs, we're going to return the table we get by converting those. So actually the definition is actually pretty simple now. All of the hard work is done by the table function. Let's just compile that. Let's just not use sized arb table, but used ordered table now. We're building it from lists now, so we don't get that problem of size explosion. So what else do we need to do? What is the property we're actually trying to achieve with this new definition that distinguishes it from the old definition? What is the good thing that we want here that we didn't have before? We must have the property that tables are correctly ordered. We've got to rule out things like this, where a smaller value appears to the right of a bigger value. Okay? So how can we check that? Well, we have a useful function that we already defined that will make it easier to check. The useful function was the function that extracted the contents from a table. Because when we extracted the contents from a table, if the things in the table are in the correct order, then they will also be ordered in the list. Because all of these things we put to the left, and all of these things we put to the right of the thing in the middle. So if you remember the definition up here, contents. Take the contents to the left and to the right. So we need to check that the contents are ordered, that they appear in order of keys. Okay? So let's define that. That the contents of T are ordered. Now, ordered is not a standard function, so we need to define it. So we have a list of things like let's define keys to be 1, 3, 5, for sake of argument. So we have these list of things, and we want to test whether these are ordered. These ones are ordered. But how do we do that? Well, we need to compare the first and the second and check that one is less than the next. 1 is less than 3. That's good. And then we need to check the second and the third and the fourth, and so on. So one way to define that is to use a recursive definition, which pattern matches on the first two elements, checks that one is less than the other, moves to the next two, and the next two. That works fine. I'll show you a neat trick, another way of doing this kind of pairwise comparison. If we compare the list of keys here with the list of drop 1 keys, let's zip those two together. So I've got the list, which is 1, 2, 3, and I've got the drop 1 of that, which is 2, 3. And I'm going to zip those two together. What happened there? Oh, something went wrong with it. I was going to zip those two things together. Let's try again. So if I zip the list and the same list but with one element fewer, then I get the two things that I'm interested in looking at. I want to compare the first and the second and the third. So that's kind of getting it in the right shape now. But actually there's a better function, and that's called zip with, which allows me not to just combine the two things with a pairing, but combine with any function I like. So what I'm going to do is I'm going to zip with the comparison operator the list of keys and drop one of the list of keys. So this will pairwise compare them and give me, in this case, both are true. And actually what I'm interested in is knowing that however long the list is, all of them are true. I do that with the function AND. So this is a way of comparing, working out that a list is ordered, just reusing standard functions. It's this guy here. So that's the thing I'm going to use. Ordered list of key value pairs. I'm going to apply that function to the keys. And what are the keys? The keys are all of the keys that we get by looking at the key value pairs taken from the list contents T. I think it's better to give that a name, key values, where the key values, okay, this is turning out to be a bit longer than I hoped for, is that thing there, so the contents. So I don't have to write contents twice, bad style. So we're going to check that the keys are ordered. Yep. Yes, it does. So it works in a similar way to dictionary order. You sort first on the first element of the pair and then on the second. So a quick but slow way of doing it here, an alternative, would be to check that the keys are equal to the sorted keys. So you're on the right track. That's another way of doing it. Okay, so I've finally defined this there. Does it compile? No, nowhere near. Yeah. So I can only do this if the keys are ordered. So I've got to add that as well. It was missing before because we weren't using the fact that they were ordered, and that was clearly wrong. So now we need to make sure that they are ordered. So let me just do a quick check again. Let's just quick check the invariant. The invariant property of table is that we only ever generate ordered tables. So really what I'm doing here is I'm testing the generator. Does the generator do what I hoped it will do? Fortunately, it does. Let me just verbose check it, just in case I accidentally forgot some type signatures. I don't think I did. No, I didn't. But anyway, by verbose checking, you can see that it's checking tables which are fairly big, actually, or reasonably big, so not trivial. All right, phew, I'm getting quite exhausted now. So we've done that. We've tested some properties. So that one's good. We managed to fix that. But there's some other stuff that still will fail. What is that? What are the other properties? That was the invariant. The invariant's good. The insert property we haven't checked. What's it called? Insert T. So it's the property of the insert function. That's where we compared it with the list insert operation. And that turns out to be bad as well. What about the other one? So we've got bugs, but we're getting there. It's the lookup function. Maybe we can do the lookup first. So the property of the lookup function seems good. So the one that we've still got a mistake in is this one. So here is where we've got the case that somebody spotted earlier. We have a table that already has the key 9 in it. And we are inserting another value for the key 9. So what should happen? Should we end up with 2 values for the key 9? Or what should we do? Well, we have to decide, but if you think about it, it doesn't make sense to have more than one Dave in the table, because you're only going to use the first one you find. So if you insert another one, it will be lower down in the table. You'll never use it. So if we insert something new, the only sensible thing we can do with it is replace. If we're going to insert a new value for Dave, we should replace the value that we have with the new value. And so there's the error then. The logic then is that if we're inserting, then we need to take 3 cases into account. The third case is when the keys are equal. The only sensible thing to do in that case is to build the same looking tree, with the only difference that we change the value to the new value. Okay? Now, let's try that again. Reload it. Try it again. Still not working. So it's still a problem, somehow related to the fact, let's try this one. If we insert T, the value 1, the key 1, 0, into the table, this table here, that ugly beast there, what do we get? We get the right answer. What we've done is updated the value 1, 4 with 1, 0. So we started with this thing, and we got this thing. It's fine. There's nothing wrong with that. But Quick Check says it's wrong. So what could be wrong? Well, it's the property that must be wrong. If it's doing what we want it to do, the mistake must be in the property. The problem here, and it's just a rather boring one, is that the insert function for lists doesn't quite behave the way we want it, because insert for lists, as we saw in our early example, doesn't always adds an extra element. If we insert 7 into the list 1 to 10, it will always add a new value. And we don't want to always add a new value. So what we need to do is filter out the 7 that occurs here. So there's a little fix we need to do in the definition here. We need to only look at the key prime, value prime pairs. Key prime, value prime taken from, let me just break this over 2 lines, it's a bit too long. We only want to apply this insert to the keys which are different from the key that we are inserting. So we want to remove that problem case. Hopefully, I really do hope now, yes, that we've now tested pretty thoroughly our definition against the basic model using lists. And that brings us to the end of what we need to do with this example. So let me just round up. So we found that bug, great. We fixed that property by hacking it a bit. Insert was not quite the right function to model what we wanted to do. Now I can summarize by saying you wouldn't actually do this in practice. You wouldn't actually build this data type in practice. You would use a standard library. It's such a common case that you would actually use a standard library. So if you were dealing with big tables and you wanted efficiency, then you would use a library of functions, data.map. Important thing to understand about the way these libraries work in these cases is that the definition of the data type, that's these things here with join and empty, are not visible in the library. You can't see them. That's internal. Because what you have is a mental model of a table and looking up in a table and adding things to a table and taking things out. It's a very simple concept. You don't need to think about the details of how that's implemented. You don't need to think about, as a user of such a data type, how the internal complicated functions are working. All you need to know is this is just like a dictionary, where we can add things into the dictionary and look up. All the hard work is wrapped up inside and invisible to the user. And the way that's done is actually by exporting from the module. The module exports the things you can use from the module, all the useful functions. It exports the type of the table. You have a type of tables, they're called map here, not table. But it does not export the constructors of the table, empty and join. So you cannot, it's impossible for you to build bad tables because you don't have the building blocks. And that's a really good thing. So hiding the details is actually a really important part of programming, building libraries of reusable components, is to hide the details that allow people to shoot themselves in the foot. And in this case, if we don't hide join and empty, you can start building unordered tables. But by only allowing people to build using the functions and not the constructors, then if you've tested your data type and tested that they always produce things that satisfy the invariant, then you will be good to go.